Hi, everybody. This lecture we will talk about the energy balance on non-reactive process. In this case, in about we talk about the energy that incorporate in the temperature change or pressure change or phase change, something like this. Sometimes we talk about the pressure change with temperature constant or temperature change with pressure constant, and also we talk about the change. For this case, we will introduce you. That's why when the species pass from one state to another cause internal energy and enthalpy for the independent of second from the first state to the second state. Because from sometimes we cannot directly determine the internal energy and enthalpy. That's why we have to check the past to get the final state. Here we will learn how to calculate both energy term as shown below. Right, we have five case. The first case, the change in pressure at temperature constant and state of aggregation. And also the second one, we consider change in temperature at pressure constant and state of aggregation. The third system, we will consider phase change at constant pressure and temperature, such as like melting point. The melting point is the process from the solid, right, transferred to the liquid phase. It was melting point. And also solidification. Right? Solidification, that's right, from liquid to solid. Yes. And vaporization. The vaporization is the phase change from liquid to vapor, from liquid to gas. And condensing is opposite, like from gas to liquid or vapor to liquid. Sublimation, that's right, from solid to vapor. This is we talk about the phase, how the energy incorporate with this. And the fourth system, we talk about the mixing. If we have two liquid or solid or two gas or liquid, or dissolving of a gas or solid in the liquid at constant pressure and temperature. Our energy incorporate with this system. And the last one, we talk about the energy that incorporate in the chemical reaction, like at the constant pressure and temperature. Before we will consider like this, we talk to you about the parts of the energy chain, right? We will call this hypothetical process part. For example, like we have phenol is solid state at 25 degrees Celsius, 180 to phenol at vapor phase, 100 Celsius and 380. But the true part, we cannot calculate delta S. We cannot calculate delta S. We don't know what is the energy that incorporates from phenol at solid state, 25 degrees Celsius, 180 m, change to phenol in the vapor phase at 300 degrees Celsius, 380. But we have no data. We cannot measure the entropy change for this case, but we can do by check the part. Okay, we can do right. We check the solid state at 25 degrees Celsius, 180 to 42.5 Celsius at 180. And also we change this is we increase the temperature as constant pressure. And also at this temperature is the melting point of solid. That's right. Solid to liquid as constant pressure. That's delta S2. Delta S1 is increased temperature from 25 to 42.5. And delta S2 is the phase change from solid to liquid. And also, and then we increase the temperature from 42.5 Celsius to 181.4 Celsius as constant pressure. This is we increase the temperature until reach the boiling point, something like this. That's right. And then we check the phase as constant pressure and temperature, right? From liquid to vapor phase. Right. This is phase change. The delta S4 is the means of phase change. And then we increase the temperature of vapor as 180 m, 181.4 to 300 Celsius 180. This is the increase in temperature at constant pressure. We get delta S5, something like that. And then we increase pressure from 180 m to 380. In conclusion, We can calculate delta S, that's right, from solid phenol at 25 degrees Celsius, 1 atm, to phenol at vapor phase, 300 Celsius, 3 atm. This includes delta S1 plus delta S2 plus delta S3 plus delta S4 plus delta S5 and plus delta S6. We get the enthalpy check that's equal to delta S. Because we cannot determine directly from this step to this step. So we don't know energy check, but we can check the path from delta S1. Delta S1 we can calculate based on the temperature change. What we talk about the sensible heat, that's right, the sensible heat. And also delta S2 is the phase change due to the melting point, right? Solid to liquid. This we can calculate the delta S of melting, of freeze, delta S of melting. That's right. It's of freezing, but it's opposite. Freezing from liquid to solid, melting from solid to liquid. And delta S3 is also in the sensible heat phase, not phase change, it's sensible heat change in temperature. Right? Delta S4 is the latent heat or heat of phase change due to the liquid to vapor, heat of vaporization. It's opposite, heat of condensation from vapor to. And also delta S5 is, it is temperature change. We can consider the sensible heat or heat change due to the increase in temperature or temperature change. Delta S6 is the enthalpy change due to the pressure change from 1 atm to 3 atm. Yes. This is show you the example that we can calculate delta S, but mostly some system we cannot directly to calculate. We can change the path with delta S is the not depending on the path. Finally, we go to from this state to this state. The entropy is the same from this path. That means delta is independent of the path. Yes. The procedure for energy balance calculation, the first step, after you draw the flow chart, after you specify and label the material balance, you specify all information, you specify the unknown. After that, you basic the calculation. And then you have to perform all required material balance calculation. It's not necessary or not. If it's necessary, you have to perform the material balance. If you cannot solve only material balance, you have to solve both material balance and energy balance. Right? Okay, for the next step, you have to consider the energy balance. Right? You have to perform or write the appropriate energy balance equation that we have derived earlier for this class, how the energy balance for closed system, how the energy balance for open system. For closed system, we will consider about the internal energy. But open system, we consider the enthalpy, because enthalpy equal to internal energy passed forward already, right? But for the closed system, there is no flow of the mass input and output. Sorry, is no flow of energy. That's right. And then if you write the appropriate energy balance equation, and then you have to delete any of the terms that are either zero or negligible for the given process. Only we have delta U or delta S, kinetic energy, potential energy, right? And also the heat and work. You have to consider if the process is stationary or closed system, right? We can drop the kinetic energy like EK and EP, and then we can neglect W if the system volume is constant. If the volume is constant, that means there is no the moving parts such as the mixing impeller or stirrer. That's like okay, we can neglect W. And also no energy is transferred or from the system by electricity or radiant. Okay, we can neglect the work. This for closed system. Okay. For the open system, at steady state, we can drop EP if the system is no appreciable vertical separation between inlet and outlet port. That means there is no the different or there is no the location different in location or the different in distance between inlet and outlet. Okay, we can drop EP, that's right, potential energy. And also we can drop WS of shaft work if there is no moving parts like pump or turbine in parallel, and no electricity and radiation. Okay, we can drop WS. In addition, if temperature change more than a few degrees, phase change or chemical reaction occur in the process. Delta EK may usually neglect. If the temperature change is more than a few degrees, phase change or chemical reaction, this process we can neglect the kinetic energy, because the kinetic energy is very small value will compare to the chemical reaction. Right? They do the heat from the chemical reaction, heat from the phase change, or heat from the temperature change. Right? The third step, after you write the energy equation and you delete some energy term, and then you choose a reference step, right? Which phase, temperature, or pressure for each species involved in the process. Because we cannot determine or measure pure form of enthalpy and internal energy, we have to calculate based on the reference step, right? Okay, some information like enthalpy and internal energy will be looked up in the table, such as steam table. Water, you can choose the steam table as the reference state to the triple point for the steam table. Right? If there are the formation in table, you choose the reference state the same information in the table. Otherwise, choose some inlet or outlet state as the reference species. So that if you select the inlet or outlet as the state, let enthalpy or internal energy for that case is zero. That case. And the first step for a closed constant volume system, that you have to construct a table column for initial and final amount of each species. But if we talk about the closed system, there is no input and output. We talk about initial state and final state. Like for the system, you have to specify amount, that's like Mi in mass or Ni in mole. Then you specify internal energy relative to the reference state Q, that's right, for the closed system. And for the open system, you construct a same table, that's right, for column, but for this case, you specify right, M dot or N dot, mass flow rate or molar flow rate, like that. And then you specify the relative to the reference state for enthalpy, right, enthalpy. Insert known value of amount of flow. I will show you the table for that case. Okay, for the step 4, that's right, you have to construct the table. Right? In table, you have the stream for the input, output for the initial state or final state. To specify the amount of mass or amount of mole. Closed system or massless or molar flow for open system. And then you specify for internal energy, that's right, for the closed system, or enthalpy for the open system. Right? And then you calculate the required value of internal energy or enthalpy, and then insert this value to the table, right, to the table. Okay, and then you know enthalpy, output, internal energy of the initial state or final state. You know mass or mole, you know massless or molar flow rate. Okay, you can calculate the energy. For example, like closed system, the closed system you consider internal energy delta U equal to summation NIGI for the final state minus summation NIGI for the initial state. Right? Or sometimes the MIUI out minus MIUI in, like this. For the open system, we have to calculate the delta U dot, that's right, enthalpy rate equal to summation NISI out minus summation NISI in, right? Or summation MISI out minus summation MISI in, like this. Okay? And then you calculate the work, kinetic energy, potential energy term that you have not dropped from the energy. And the last step, you solve the energy balance. That's right, energy balance. For the closed system, you use like this equation. Q minus W equal to delta U plus delta EK plus delta EP. For the open system, Q dot minus W dot equal to delta S dot plus delta EK dot plus delta EP dot. Right. Mostly when we talk about the closed system, there is no energy transfer between the system and surrounding. There is no flow. Like this. Okay, we talk about the amount. For open system, both mass and energy can transfer. We talk about the flow rate, mass rate, or molar flow rate. Okay. We give you an example. Right? We talk about the acetone denotes as AC. It partially condensed out of a gas stream containing 66.9 mole percent acetone vapor, and the balance is nitrogen. Nitrogen. And the process, speculation, and material balance, that's right, are shown in this. This is the information. We feed 100 mole per second of acetone vapor with 66.9% and 33.1% of nitrogen. It is in the vapor phase at 65 degrees Celsius 180 atm to the condenser. After the condenser, partial condense of acetone. The acetone will condense to be the liquid phase. For this case, we have the phase change, that's right, or the condensation with 63.55 mole acetone per second is condensed at 20 degrees Celsius 580. And another stream is the vapor form. It includes acetone and nitrogen at the same temperature, 20 degrees Celsius 580. And threshold mole is 36.45 mole per second. And the fraction for acetone and nitrogen as shown in this. And also for condenser, we have some energy transfer. As I mostly for the condenser, the energy will transfer from the system to the surrounding. I transfer from system to the surrounding. But for this case, if you use this formula, that's right, this formula we balance based on energy input is positive value. Okay? If you use this formula, the energy will input. Okay? And you have to write input Q is input. For this formula, we create what we balance, set up the energy balance based on Q input. It is positive. You input the positive. And if you solve the equation and then you get Q is positive, okay, mean Q is input. And then after you solve the equation and then you get Q is negative, you mean the Q is output. For this case, we have calculated the cooling requirement. You get this Q should be minus value. Q should be minus value because the cooling mean Q is transferred from the system. But the equation based on Q input to this. The first step, you have to perform the material balance calculation. After you draw the flow chart. For this case, no, not necessary. That's right? Not necessary to balance the material because the material is balanced already. The input mass total is 100 mole per second. Output is 36.45 and 63.55. It's the same. Input equal to output. Steady state balance. The total mass is input minus output plus generation minus consumption equal to accumulation. For that case, the total mass is no generation, no consumption. And for this system, flow in and flow out, there is no accumulation. That's input equal to output. Okay. For this system, the material is balanced already. The next step, you have to write the energy balance. For this case, is for the open system, you use this equation. There is no shaft work, there is no pump, there is no impeller, there is no turbine. Okay, you can cancel this. And there is no the moving parts, and there is some change in temperature. Very much. I have phase change, we can cancel right the kinetic energy. And there is no the difference in the distance or the vertical in the vertical direction. There is no potential energy, and then you get Q dot equal to delta S dot, which we know delta S dot is summation Ni Si minus Ni Si in out minus in. Right? It is the second step. The third step, you have to choose the reference state for acetone and nitrogen. Okay. For acetone, that's right. The acetone, we have the information of acetone in table. For this case, you can choose the acetone in liquid or gas phase at the reference state. The mode system we choose the liquid or solid at the reference state. For this case, we choose acetone at the output state in the liquid phase at 20 degrees Celsius 5 atm at the reference state like this. We choose the output acetone in liquid phase at the reference state for acetone. And how about nitrogen? The nitrogen we have the table. So write in table BS as specific entropy of nitrogen. We have the information in table. You can choose the table at the reference state. The table, the reference state is 25 degrees Celsius and 180. Let's get nitrogen, we choose the reference state at 25 degrees Celsius, 1 atm at the third step, we choose the reference state already. Acetone is liquid phase at 20 degrees Celsius. For nitrogen, it gas phase at 25 degrees Celsius, 1 atm. Let's get the first step. You contract the table. Right? The reference state, you know the reference state as acetone liquid phase 20 degrees Celsius 1 atm. Nitrogen gas phase 25 Celsius 1 atm. And then you contract the table. The first column should be right or the substance. Okay. In this case, we have acetone in vapor phase, acetone in liquid phase, and nitrogen in gas phase. Okay. And the second and the third column, you draw about the mass or mole. For this case, open system, we talk about the mass rate or molar flow rate. For this system, we talk about the molar flow rate. That's right. N dot I, the input mole per second. And the third column, we talk about the enthalpy. That's right. Enthalpy input is the kilojoule per mole. And the fourth column, we talk about the molar flow rate of output. Right? And the last column, we talk about the enthalpy of output. Okay. For acetone vapor, the input acetone vapor is 0.669 multiplied by 100, you get 66.9 mole acetone per second. This is 66.9 mole acetone per second. And we denote as S1 or enthalpy of acetone. Okay. Acetone vapor output. Acetone vapor output is about 0.092 multiplied by 36.05. You get 3.35 mole per second of acetone vapor output. And we denote S3 as entropy of acetone. And then we consider acetone liquid. Acetone liquid, there is no acetone liquid in input. Okay. There is no input acetone. No. About output, we have acetone output. Right? It's 63.55 mole acetone. How about the entropy of acetone? Entropy of acetone output is 0 because we shoot the acetone liquid phase at 20 degrees Celsius and 5 atm at the reference. In this case, acetone is 0. Entropy of acetone is the reference. Okay, the next step we talk about nitrogen is gas phase. Nitrogen input is 0.231 multiplied by 100, you get 33.1 mole acetone or mole nitrogen per second. Yes. And we denote S2A is the entropy of nitrogen input. And nitrogen output, input equal to output for nitrogen. It's 0.908 by 36.45. And denote S4 is the entropy of acetone. Okay, the next step we have to determine S1, S2, S3, S4. S2 and S3 you can list from the table because the table for acetone is referring to this temperature and pressure already. And how about S1 and S3? S1 and S3 you have to calculate based on referring to acetone liquid output. That's 20 Celsius and 5. We show you the first step for S1. S1 is the specific entropy of acetone vapor phase at 65 degrees Celsius 1 atm. it relative to the reference state with acetone liquid at 20 degrees Celsius for ATM. This case is delta N free for acetone liquid at 20 by ATM to acetone vapor. That's right. Because we reference acetone vapor at 65 1 ATM to acetone liquid 20 Celsius 1. We cannot calculate or we cannot data information for enthalpy from acetone 20 degrees Celsius liquid 5 atm to acetone vapor phase 65 Celsius 1. For this case, you have to the input for this example, right? Hypothetical process part. This. For this case, the first step you have to change the pressure. That's right. Okay. You have changed the acetone liquid phase at 20 degrees Celsius from 5 atm to acetone liquid phase 20 degrees Celsius. It is constant temperature from 5 atm to 1 atm. Delta S1 is the entropy that change of pressure. And then you change the temperature from 20 degrees Celsius to 56 degrees Celsius at 1 atm. For this case, because we know the boiling point of acetone at 56 Celsius at 1 atm. This is the normal boiling point of acetone. Okay, we have to change from temperature at 20 to 56 first, and then the phase change at constant temperature and constant pressure. Delta S1B is the change of temperature as constant pressure, and delta S1C is the change of phase change as constant pressure and temperature. Right? Okay. After you get the vapor acetone 56 degrees Celsius 1 atm, and then you change the temperature as constant pressure because our state is vapor 65 Celsius 1 atm. Okay, we change from 56 degrees Celsius 1 atm to 65 Celsius 1 atm, and that is the entropy of temperature change as constant. Okay, and then you calculate for each system is the delta S1A. Delta S1A is the entropy change due to pressure change. Right? For this case, for the change in pressure, if the liquid or solid, that's right. If the liquid or solid, delta S equal to V delta P. For that case, delta U equal to 0. For this case, is the liquid phase. That's right. For the liquid phase, delta U equal to 0 if the pressure change because internal energy independent of pressure. Right? Okay. If pressure change, delta U equal to 0. Right? If delta U equal to 0, you can calculate delta S. Delta is equal to delta U plus delta PV. That means it's 0. You get V delta P. If V constant, you get V delta P. That's right. And then you can calculate enthalpy. For this case, we know right the volume. We multiply the molecular weight of acetone and divided by density. This is molecular weight of acetone. This is the density of acetone. You get specific volume. Is 0.0734 liters per mole for the first step. Right? And for the second step, the second step is acetone liquid to acetone liquid as constant pressure, but change in temperature. For this case, we call about the sensible heat. Entropy is incorporated in terms of sensible heat and the change of temperature. But for this case, we can put it in this term. Entropy is the integration of temperature Cp dt. Right? Integration from T1 to T2 Cp dt. Cp is temperature dependent. For this case, it's constant pressure. Mostly, we have some information about the Cp of the chemical. So in table in our book, for example, acetone liquid phase, it is the entropy Cp, that's like specific heat capacity or heat capacity at constant pressure. We call it Cp. Cp in kilojoule per mole degree Celsius is equal to this term, right? And for vapor, equal to this term, and then if you know Cp, you insert Cp and then do integration. It is the second step, and calculate entropy based on the change in term of integration Cp. And then the first step, delta S1c. Delta S1c is the delta S of vaporization, something we call latent heat of vaporization. That's constant temperature and constant pressure. The most we have in data in table, like for this case, the most data in table B1 is book. There is some boiling point of acetone. Boiling point of acetone is 6 degrees Celsius. This is the more boiling point. And also, in this case, we know like the delta S of vaporization is 30.2 kilojoule. 30.2. Okay. And then the last step, right? We know right the acetone as vapor phase 56 degrees Celsius 1 atm to acetone vapor phase 65 degrees Celsius 1 atm. This for temperature change at constant pressure. We call about the Cp also. In this case, we talk about the Cp. Like the acetone vapor from 65 degrees Celsius 1 atm reference to acetone liquid. This for the this is for S1. That's right. Here the S1. And then you can calculate S1 equal to delta S1A plus delta S1B plus delta S1C plus delta S1D. That's right. This is the pressure change. This is temperature change. 1B and 1D. That's right. 1D and 1B. You use this Cp for 1B. You do this Cp for 1D. That's right. It's for the vapor phase liquid. Okay. For this case, delta S1A equal to V delta P. That's right. V delta P. Delta P is 1 atm minus 5 atm. That's right. Change from 1 atm to 5. From 5 atm to 1 atm. Or to 1 minus 5. And the second term is from 20 to 56. That's right. It's the liquid phase. This is integration from 20 to 56 Cp acetone liquid phase dt. This. And the third term is heat of vaporization. That's right. Heat of vaporization. And the last term, that's right, it change from 56 to 55. That's right. This is the vaporization. Substitute it. That's right. You substitute it. And then you calculate for the first one. Delta is 1A. That's right. This is the V delta P. This is the volume delta P. And this is the conversion unit. And then you get 0.02 0.02. For this case, is have some minor value. And then the second term is the integration from 20 to 56. And then you substitute Cp of liquid phase. Get this term. After integration, that's not integration, you get this term. And you substitute value from 20 to 56, you get answer. Or the S2, 1, 2, S1A, 1B. And then the S1C is the heat of vaporization. You can open from table B1. Right. For the fourth term is the S1D is the phase temperature change for the vapor phase from 56 to 65. That's the Cp of the gas phase. This term. And then the integration and substitute from this is I forgot to change. Sorry. This integration from 56 to 65. Right? get this value. And then you know data S1A, data S1B, data S1C, data S1D, and then you calculate S1. That's a bit you get 35.7 kilojoule per mole. Okay. Now you know S1. Right. You know S1, and then you know S3. Right. You know S1 already. Okay. And then you calculate S3, S2, and S4. How about S3? S3 also is the same like previously. S3 is acetone vapor output at 20 degrees Celsius 5 atm, referent to acetone liquid phase at 20 degrees Celsius 5 atm. In this case, you write to the same previously technique. You have to change the pressure from liquid 20 degrees Celsius 5 atm to acetone liquid at constant pressure, at constant temperature, right? From 5 to 180. This data is 3A. And the next step, you increase the temperature to the boiling point. That's right, to the boiling point. You get like this, from 20 degrees Celsius to 55 degrees Celsius, 180 m. It's 3B. And then you vaporize at constant temperature and pressure. You get data S3 series, the evaporation or heat or vaporization. And then you check the temperature or change the pressure from vapor at constant temperature from 180 m to 580 m. And the last term, you change temperature as constant pressure, right? 56 to 20. You have 1, 2, 3, 4, 5 terms. That's right. The first term you get the same previously. It is the same previously. And also it's the same previously. For this case, you have the change in pressure. That's right. From 5, this is from 1 to 5. It's the same. That's right. But it's opposite in terms of the direction. Previously we form like from 5 to 1, but for this case from 1 to 5. And then the last term is the change in temperature. That's like from 56 to 20. You get this result for ST. Right? Get this result for ST. And the last two terms, S4, right? This is S2 and S4. S2 is nitrogen input at 65 Celsius. This is N2 and N4. N2 and N4, we have to change this N2. N2 is the nitrogen gas at 65 degrees Celsius. For this table, you have only like 0, 25, and 100 degrees Celsius. For 65, you have to interpolate between 25 and 100 degrees Celsius. It's the enthalpy between 0 and 2.19. After linear interpolation, you get 1.16. And S4 is the nitrogen at 20 degrees Celsius. Right, 20 degrees Celsius. It located between 0 and 25. The value is minus 0.73 and 0. And then after you interpolate like linear interpolation, you get 0.1. It's minus 0.1. And then you get S1, S2, S3, and then you substitute this term in the table. Right? You substitute all terms in the table. S1, S2, S3, S4. For this case, you know N in, S in, you know N out, S out, all of the stream. And then you calculate the delta S. Delta S equal to summation Ni Si of the output stream minus summation Ni Si of the input stream. For the output stream, that right, we have 3 terms. That's right. 3.35 multiplied 22, 32. This case. like mole per second, kilojoule per mole, you get kilojoule per second. This is the energy rate. The second term is 63.55 multiplied 0. And the third term is 33.1 multiplied minus 0.1. And then minus in the input term we have 2. That's right, minus 66.9 multiplied by 35.7. And the last term minus 33.1 multiplied 1.16. And then you get the enthalpy, right? Delta S equal to minus 2320 kilojoule per second. That's right, kilojoule per second. And then you substitute in the equation like that. Know this term, but for this case there is no work, no kinetic, no potential energy. That means Q dot equal to delta S dot. And now you get Q dot equal to delta S dot, which equal to minus 2020 kilojoule per second. Right. Kilojoule per second means kilowatt, because watt is joule per second. In this case, you get heat equal to minus value. This means heat is out of the system. Because the energy equation that we balance is based on Q input. But after you solve the energy, you get minus value. That is mean the Q is transfer from the system to the surrounding. Okay, the answer is the cooling rate is 2322 kilowatt. That's why you did not answer in the minus sign or positive sign, but the minus sign or positive sign indicate only the his input or his output. For this case, his output. That is correct because it's the cooling system for this example. Okay, this is the general energy balance that we talk about the phase change, we talk about the temperature change, we talk about the pressure change. Yes, if you talk about the pressure change, we call about it delta S, delta U equal to the delta S plus P delta V. That's right. For something, we talk about the temperature change, we call the specific energy. That's right, or specific heat energy. And if you talk about the phase change, something we talk about the evaporation, melting, condensation, freezing, or sublimation, something like this. Okay. In this case, we will recall about for the previous example. We talk about the previous example. We have some system. We talk about the pressure change as constant temperature. In this case, if the pressure of solid or liquid change as constant temperature of the solid liquid, we assume that delta S is approximately 0. Delta U, sorry. For the solid liquid as constant pressure, we assume internal energy is equal to 0. When the internal energy is equal to 0, delta S equal to delta U plus delta PV equal to V delta P. That's right. If V constant, P is change. That means delta S equal to V delta P and delta U equal to 0 for liquid and solid system at constant temperature with pressure change. And for gas, especially for ideal gas, delta U and delta S are independent of pressure. That means at pressure constant, delta U and delta is approximately 0. That's right, for ideal gas. But if the gas at temperature well below 0 or well above 1 atm are involved, this means we talk about the real gas. We have to use the table for delta U and delta S. That's right, for this case. We cannot assume delta U equal to 0 and delta S equal to 0 for real gas. Or the system at 0 degrees Celsius is below at 0 degrees Celsius or above 1 atm. Okay, for this case, we concluded for pressure change with constant temperature for liquid solid, delta U equal to 0, delta S equal to V delta P. And for ideal gas, delta U delta S equal to 0. For the second system, we talk about the change temperature at constant volume. For this case, we consider the sensible heat. The sensible heat is the heat that must be transferred to rise or lower the temperature of a substance or a mixture of substance. For this case, as constant volume, we require CV. But CV is the limit at delta T approach 0 of delta U divided by delta T. If the delta T is very, very small value, we can check from delta U divided by delta T equal to du divided by dt as constant volume with derivative of U with respect to temperature as constant volume. That's right. In this case, we can arrangement the equation du equal to cv dt, and then you can integrate cv dt from t1 to t2. That's right. Finally, if we have the system right for a at t1 v1 to a at t1 v2 and a t2 v2. For this case, this is the constant temperature. That's right. Constant temperature and change in volume. Right. And the second step, this is constant in volume temperature change. You can recall for this term, and for this term is u equal to delta h for at v delta p. For this case, we have two terms, right? Okay. For this case, we have two terms, right? The first step, the temperature is constant. V change is delta u equal to delta s at v delta pv. For this case, that indicates cv dt. Delta u1, delta u2. Mostly that's right. Get delta u1, delta u2. For ideal gas, that's right. Delta u equal to 0. Delta equal to 0. Delta u1 is equal to 0. You get delta u is approximately cv dt. cv dt. And also for solid or liquid, you get this also. Or constant volume. That's right. Constant volume. Okay. For ideal gas, that's right. Liquid, solid, U it depend only on temperature. So that's in the T constant. What does it mean? T constant delta U is equal to, for this case, T constant delta U equal to 0. It's the same this that line. It's the same detail for liquid and solid. That's right. At constant pressure, we change delta U equal to 0. The same. For this case, the delta U is equal to integrate cv dt for ideal gas or solid liquid, or delta U equal to 0 for the first step. Equal to 0, you get delta U2. A change in temperature. Non-ideal gas equal to this only when V is constant. We can use this equation. Ideal gas, solid liquid, and ideal gas at V constant. For example, calculate the heat required to write 200 kg of nitrous oxide from 20 degrees Celsius to 150 degrees Celsius in constant volume. Let's say. For this case, the constant volume heat capacity of nitrous oxide expressed in this equation. It is Cv of nitrous oxide. For this case, we can approximate it is the nitrous oxide. That's right. It may be gas phase. For gas phase, you can use this data U equal to like. That means delta U equal to indicate 20 to 150 degrees Celsius Cp dt. That's right. You substitute Cp. And then integration. Get this answer. Right? Integrate 0.855 dt, did integrate constant, you get 0.55 t. That's right. Integrate constant multiply t dt is equal to t squared divided by 2. For the first term, integration is 0.855 t from 20 to 150. And the second term equal to t squared divided by 2 multiplied by the constant. And then you substitute 20 to 150, you get this answer. That's right, you get this answer. And finally, energy balance for closed system. For the energy balance for closed system, that's right, you use the energy balance for closed system. It is for open system. Right. For closed system, you use this. In this case, there is no work, no kinetic energy, no potential energy. Q equal to delta U. Q equal to delta U. You get the answer. Get the answer. And then you substitute the specific internal energy. Specific internal energy means the energy divided by mass or mole. For this case, divided by mass. You multiply mass, you get energy in terms of heat. 24,200 kilojoules. For previous case, we talk about the change in temperature but constant volume. But the next case, we talk about the constant temperature as change in temperature as constant pressure. Because it's the heat capacity as constant pressure, we know as Cp. General note for this case. For Cp, that's right. Cp is definition by limits of delta T approach 0, delta S divided by delta. As very small value of delta T, we change from limit to derivative of S with respect to temperature at constant pressure. And then you rearrange the equation, you get ds equal to Cp dt, and then you can integrate. That's right. You can integrate ds from 0 to s, you get delta s. That's right. This is the integrate ds equal to delta s. Right. This means s2 minus s1 term of delta s. And then you integrate Cp dt from T1 to T2. For this case, we separate into system. From A at T1, P1 change, A at T1, P2 is pressure change. That's right. Is pressure change, constant temperature, delta S1. And A T1, P2 to A T2, P2, this constant pressure change in temperature. This is called for Cp. That's right, for Cp. For this case, we consider like the first one for delta S1. For delta S1, at temperature constant pressure change. For this case, delta U equal to delta S plus delta PV. That's right. For ideal gas, delta S, delta U equal to 0. That's right. For ideal gas. This is for ideal gas. But for solid or liquid, delta U equal to 0, you get delta S equal to V delta P. As I talked to you earlier. For this case, delta S equal to delta U equal to 0 for ideal gas. But for solid or liquid, delta U equal to 0, that you get delta S equal to V delta P. Because you know delta S equal to delta U plus delta PV. For the V constant, you get V delta P. And the second term, delta S2, is integration of this term. Finally, we can conclude that for ideal gas or non-ideal gas at P constant is only delta S2 only, indicate Cp dt. But for solid or liquid, delta S1 equal to V delta P plus delta S2. That's right. This is the general equation for Cp. That's right. For Cp. This should be pressure. Sorry. And then you know, right, the relationship between Cp and Cv for liquid and solid. Cp and Cv is equal. For liquid and solid, Cp equal to Cv. But for ideal gas, Cp equal to Cv plus ideal gas, Cp equal to Cv plus. Okay. Before I show you the example, I will stop the lecture now and we continue later. Thank you.